in Pharmaceuticals in association with Higher Secondary Principals Forum.
Good morning, dear students, and welcome to the enlightening chapter on light. Let the light of knowledge reach far and wide. The intricacies of light has been studied over the years. It is because of the light and the sense of vision that we can see the beautiful world around us. So, my dear student, I am Mrs. Bhakti Bandekar, will be taking up the chapter 9 of the NCERT syllabus, that is the ray optics. How do I put it in words, the beauty of this chapter? Yes, indeed I am saying it's beautiful, and why? Definitely you will come to know as we are moving across it. In this particular chapter, you will be learning about the interesting and the magical phenomenon. You will be learning about the mirrors, lenses, prism, optical instrument, and so on. So students, let's get started. So to start off with, we'll be learning about the reflection of light. Now what it is? It's the bouncing back of the light in the same medium when it strikes a surface. So there's a key word, students, you need to know bouncing back. So let out over here, I have got the mirror, and as you know, the one becomes the reflecting and others, the back of the mirror is painted or the silvered. Over here I have got my incident ray, which is incident at a particular point on the mirror. So that's your normal which I have drawn, and here you are the reflection of light, that is the bouncing back of light in the same medium. So incident ray, and how do I get my angle of incidence? It is the angle between the normal and the incident ray. So this is your angle I. Next, your angle of reflection, that is angle made by the normal with the reflected ray. Now let us move on to the laws of reflection. So what does the law says? A very important, the first one, it says that angle I equals to angle R, meaning these two angles, they are equal. Second, it talks about the rays, that is the incident ray, the reflected ray and the normal all are coplanar. Coplanar means they lie in the same plane. Now let us move on to the image formed by the plane mirror. You all must have seen yourself many a times in the plane mirror, and you know how is the image formed. Let us first check out the ray diagram. So here I have got the mirror. I have the image being placed in front of the mirror, and there you have the incident rays. The red ones are the incident and the green ones are the reflected rays. And as you can see, they are not meeting up over here to get an image. So we need to produce them backward. So here we have produced the rays, the reflected rays backward, and over here it is a point where all the rays are meeting. So definitely we will be having our image over here, and this particular image is known as the virtual image. Why? That is because it is formed behind the mirror. If the image had to be in front of the mirror, it would have been a real image. So right now this is the virtual image. So a plane mirror forms a virtual image. Now let us check out the characteristics of the image. Now students, you have seen yourself many a times in the mirror. So what do you think? How is the image formed? Do you see yourself a big flattened or in a big size? Yes. Or do you feel your legs on top and the heads down? How is the image? Right? You have seen, you have used the plane mirror. The first, you see yourself of the same size, isn't it? So that's the first thing. The image in the plane mirror is of the same size as that of the object. Next, it is at the same distance behind the mirror as it is in front of the mirror. And the third characteristic, it is virtual. I explained you that why it is termed as virtual. It is erect. As I have said, you can see your head and your legs at the proper places and not inverted. So, that is meant by the erect, and it does suffer lateral inversion. Now, what is lateral inversion? I have got a picture for you all, with that it will be clear. So, what you can see, students, check out. I have got the letters and the image which is in the mirror. So, this is termed as the lateral inversion. You can see the word physics in the mirror. So, that is how it looks, and that is how is what we term as the lateral inversion. So, this was the image formed by the plane mirror. So, you know that a mirror is a reflector of light. The question arises, is only mirror a reflector of light? Its answer is no. Each and every object reflects the light. You and me, we are the reflectors of light. You can see me and I can see you because we are reflecting the light. So, each and every object reflects the light. Now, this was about the plane mirror. Now, let us move on to the spherical mirrors. Now, what does that mean? Here, a spherical mirrors, they are the part of a sphere. You can think this as a sphere, visualize it as a sphere. So, if I slice it, I am going to get a mirror, and a concave mirror is the one in which the outer part, the bulging part is silvered and the inner part becomes reflecting. You can see over here, this is the back of the mirror and this is the reflecting side. So, that is how we get a concave mirror. Now, what about the convex? So, this is a sphere, you imagine it as a sphere, and here is the center. If I slice it and I use this part such as the outer and the bulging part is reflecting and the inner is silver, then we term it as the convex mirror. So, this is how you get the concave and the convex mirror. So, there are few terms which we will be using throughout. So, let us go for it. So, I have got the concave mirror, a convex mirror. By now you know how to draw it. A line which is passing through the pole is termed as the principal axis, and the pole is the midpoint of the mirror. Now, we know the center. I showed you all the center of the sphere. So, this center of curvature is the center of the sphere of which the mirror is a part of, and this distance from the pole to the center is your radius of curvature. So, these are the terms which we will be using throughout. Now, let us go for the principal focus. For a concave mirror, you can see we have the parallel rays parallel to the principal axis, and after reflection they meet up at a particular point. So, this point where the rays have been converged is termed as the focus. So, you can see a concave mirror is a converging mirror. Why? Because it converges the light at one point. Let us move on to the convex. So, for a convex, back again we have got the principal axis. The rays are hitting the mirror, and if you see, the rays are being diverted. The rays are not meeting over here, so we need to produce them behind, and this point is where all the rays are meeting up. So, this will be termed as your principal focus. So, what you can say about the convex? Yes, it is a diverging mirror. That is because it has diverted the rays. So, these are the two things which you need to know. It is in concave, converging, convex is the diverging. So, let us move ahead. Now, let us check out how is the image formed by these two mirrors. So, with regards to concave, I have told you it is converging, and a concave forms an inverted image or magnified and upright. So, having known this, that it is forming a magnified and upright, I have shown you a figure. So, what you can see? You can see a lady and With her hand she is using the concave mirror, and isn't it she is happy to see the bigger magnified image, isn't it? So even you can play with it, it's a nice thing to see something bulging, something magnified. So this is how is the image formed in a concave mirror. Now what about the convex? Convex is the diverging mirror. It always forms an upright and diminished. So I have got a picture over here. This is the side mirror, and what you can see? You can see the image, but it is the diminished size. Okay, it is a smaller inside and it is upright. Yes. So this is how is the image formed in a concave and a convex. Now you all are at home. So what do you think, how you will check out the convex and the concave? There is an easy trick, students. You can go to the kitchen and grab a spoon. You can hold it in your hand, and there you will be having your concave and the convex. So you can see in the spoon there is a inner side, it is depressed, and this is the bulging. So this becomes your concave and this becomes your convex. So please check out the images formed in both of this concave and the convex. So you have it at your place. So now I know how is the image formed. So let us check the applications. I need to apply it. So let us go for the applications of it. Concave mirror. Now there you have got the picture, and you know it is used by the dentist, isn't it? That is because I know I am going to get a magnified image when I am using my concave mirror. So it is commonly used by the dentist, and it is preferred over the plain mirror for the shaving and the makeup purpose. So these are the applications. You all must have even seen this mirrors when especially using for the makeup and the shaving purpose. Moving on for the convex, you are definitely must have noticed this at the road intersections. Now it has been installed to get a wider range so that we can know the oncoming vehicles. So next time you go out and you figure out this, you know it's a convex mirror. And why the convex mirror is used? That is because we get the diminished image, and because of that the field view increases. So here we have wherein we need a bigger field view, we always use a convex mirror. The side mirror, it is also called as the driver's mirror. So these are the applications of the spherical mirrors. Now we have got some sign conventions which we need to know in order to solve the problems and the derivations. So I will just quickly go through it. So over here I have got the concave and the convex mirror, and I have got the principal axis, I have the pole, center of curvature, and this distance is termed as the radius of curvature. So that is your radius of curvature. The distance between the focus and the pole is given as the focal length. Now for a concave, and this is the direction of the incident light because this becomes reflecting, and for a convex this is your incident light. So this becomes the reflecting. So what is the first thing? The first thing says that all the distances are measured from the pole. So we need to start measuring from the pole. Second, if you are measuring in the direction of the incident light, the measurements are taken positive, and if you are moving in the opposite, the measurements have been taken as negative. Upward distances are taken as positive, whereas downward are negative. So where is your upward? Is here. Can you see this? So these are your upward will be taken as positive, and this is your downward which will be taken as negative. So this sign conventions are important while solving the problem. Now if we see this, what you can conclude? My incident light is in this direction and I will be measuring my readings from the pole. So you know both are in opposite directions. So I need to assign a negative sign for the focal length and the radius of curvature when I am dealing with the concave mirror. What about the convex? Incident light is in this direction, I need to measure from the pole. So you see that your focal length and R is going to get a positive sign. So please remember students, the moment you have the concave mirror, you will be having the negative sign, and for the convex, F and R is going to be the positive. These are the simple sign conventions which you need to remember. Now we have got the first simplest derivation, a very simple, that is the focal length of the spherical mirror. So let's get started. We have got the concave mirror. So this is the first ray that I am using. It is the parallel to the principal axis. The reflected ray goes through the focus, and I have drawn the normal at the center of curvature. This is the construction that has been done. So this is a D, wherever all they are meeting is M, that is the pole. Now this is your angle of incidence which I have given as theta, and by the laws I know even angle of reflection is going to be theta. So this is going to be theta, and this is the 2 theta. So this is the figure. Now let's start with the derivation, a simple derivation, a short derivation. So tan of theta, use it over here, that is this particular triangle MDC. Tan of theta is going to be MD upon CD. Next, tan of 2 theta is going to be this triangle, it is MD upon FD. Now we can have a simplification as for a small angle theta is going to be tan of theta as theta and tan of 2 theta as 2 theta. So let's substitute this in the above equation. In place of theta I can substitute whatever I have got. So ultimately this is what we are going to get. So MD upon FD equals to twice of MD upon CD. So I can cancel out MD from the numerator. What remains is FD equals to CD by 2, and you know FD is a distance from the focus till the pole. You can say D and P are very close, so I can say it is F, and CD is the radius of curvature. Using this I have got my final expression, that is focal length is the half of the radius of curvature. So this is what we will be using ahead, that is focal length is going to be half of the radius of curvature. So this was a small and a simple derivation. Now we are moving on to a major derivation, students. Okay, it's really important derivation. So let us start with the ray diagram. So concentrate on the ray diagram, students. I have the concave mirror. I am finding the mirror equation. Mirror equation relates the object distance, image distance and the focal length. And how is the relationship? At the end of the derivation we will get to know. So I have here object AB which is placed at a distance u, and I have chosen 3 rays. Now let us check each one of them. So over here the first one is parallel to the principal axis. After heating the mirror it goes through the focus. So there it is. Second, from the object it is heating at the pole, and then it goes as per the laws of reflection. The third, passing through the center of curvature, it hits the mirror and it retraces the path back. So I have chosen these 3 rays, and wherever the 3 reflected rays are meeting you are going to get your image. So here is a point where you are going to get your image. So what you can say about the image? Since it is meeting in front, it is a real image, and it is going to be an inverted image, and it is slightly diminished. Okay. So this F is the focal length, distance between the focus and the pole. B is the distance from the image to the pole, and object is the object distance from the object to the pole. So this is about the ray diagram, and it's very important. Check out the rays. Your arrows are important for every ray diagram. So let's start. So I am using my first triangle, that is A dash, B dash F and MPF. As they are similar, I can write this equation as the ratio of their sides are equal. That is B dash A dash upon MP is going to be equal to B dash F upon FP. Now instead of PM, which is over here, I can use AB, that is because PM is equal to AB. So this is my first equation. Now let us go for the second. So I have considered the next triangle, that is A dash B dash P, that is this one, and ABP, which is similar. And since they are similar, I can write this particular equation that says B dash A dash upon BA is equal to B dash P upon BP. So these two equations are important. This is the start of your derivations. So I have considered the triangles to be similar, and hence I have got equation 1 and equation 2. So you can check out, I can compare the equation 1 and equation 2. What you can see, one side, that is the left hand side, is same, so I can equate the other side, and this is what I will be getting by comparing both the equations. So B dash F, I have written it as B dash P and FP. So why? You can check out over here, that is B dash F, I can write it as B dash P minus FP. So that is why I have written it like that, equals to B dash P BP. Now using the sign convention, I just spoke about the sign convention, students. So B dash P is the image distance, so it is minus V because it is a concave. Over here FP is minus F, BP, which was the object distance, is minus U. So substituting in the above equation, instead of B dash P, FP and BP, I will be substituting these. This is what I get. So it is minus V plus F minus F equals to minus V upon U. So you can cancel out the negative sign. From here to you can cancel out by taking it out. So this is what I get. Now a simple mathematical steps you have, and this is your mirror equation, that is 1 by F equals to 1 by V plus 1 by U. So this relation is known as the mirror equation, where V is the image distance, U is the object distance, and F is the focal length. So this was a major derivation known as the mirror equation. Very important formula, students, you cannot forget it. You need to remember this. So let's go ahead. So moving on to the linear magnification. Now what is linear magnification? It is the ratio of height of the image to the height of the object. So M, I have given it as h dash upon h. Now h and h dash will be taken as positive or negative as per the sign convention, and I have already told you all how do we take the sign convention. Now same way as we had done previously, I have taken A dash, B dash P and ABP, which are similar, so I get this particular equation, and with the sign convention I know this is my image distance, this is the object distance, so I have taken it, I can cancel out the negative sign, and finally what I get is this. So your magnification is going to be h dash upon h, that is the image upon the object, is minus V upon the U. V is the image distance and U is the object distance. So this is about the linear magnification of the concave mirror. So students, this was all about the reflection. So let us go for a problem. Okay, simple problem and a short problem, which is from your textbook. So over here I have got an object which is placed at 10 centimeter and 5 centimeters, and I am using a concave mirror. Radius is given as 15 centimeter. You have been asked to find the position, nature and the magnification. So the object is placed at two different distances, radius of curvature is given, and we need to find the other things. So let us start. The moment I know it is a concave, using the sign convention I need to place a negative sign, and I know focal length is half of the radius of curvature, so I can use it, and I am getting the focal length as minus 7.5 centimeters. Now object distance is U, I am taking the first one, so it becomes minus 10 centimeters. I can use now the mirror equation. substitute and get the answer for V, which is given as minus 30 centimeters. Now, images at 30 centimeters from the mirror on the same side. Now, how do you come to know it is same side? That is because of this negative sign. You know the sign conventions for a concave FR, because and if the image is formed in front of the mirror, it is going to be negative. So, here it is forming on the same side. So, I can say it is the real image. Now, taken the magnification, I have already told you all the formula, it is minus V upon U. So, V I have got as 30, U it is already given as 10. So, answer is minus 3. So, this again tells you it is an inverted image. So, finally, the nature and the position is magnified, real and inverted in the first case. Let us go for the second. Second, you can see it is a 5 centimeter, it is at 5 centimeter. So, I am choosing my object distance as minus 5, substituting in the mirror equation, and this is the answer, that is plus 15. Now, what the plus sign tells you? It is going to tell you that you need to produce it behind, it is going to be a virtual image. It is not in real, it is a virtual image, and magnification again you get it 3. So, that tells you it is a plus 3. Is going to be magnified, virtual and erect. So, have you seen we are getting two different results for the two different positions. So, this was a simple problem based on the mirror equation. Hoping you all have understood it. So, this was all about the reflection. Now, let us move on to the refraction of light. Now, what is refraction? Refraction is the change in the direction of the path of light when it undergoes or when it encounters another medium. The moment the ray encounters another medium, it is going to change its path. So, let us check out with the figure. So, I have the incident ray which is incident at an interface. It is the upper, you can say it is an air, a rarer medium, and then it is going into the denser medium. So, it has encountered a medium, another medium, it is going from the rarer to the denser. So, check out students, I know at the point there will be slight reflection, but the remaining is going to get refracted. So, this is going to be the refracted ray, and you can see there is a change in the path. In absence of the medium, this ray will have travelled it straight, but the medium has refracted the ray, that is there is a change in the path. Now, same as the laws of reflection, we need to even take care of the laws of refraction. So, the laws of refraction talks about the similar thing, as it says that incident ray, refracted ray and the normal to the interface all lie in the same plane. Now, what does that mean? You can have a look at it. Over here we have got the plane, and all these three they are lying in the same plane. Down the next, so one of the important is says sine of I upon sine of R equals to n to 1. n to 1 is the refractive index, is a constant, and is known as the refractive index of second medium with respect to the first. Now, this particular formula is commonly known as the Snell's law. So, as n to 1 is the refractive index of the second medium with respect to the first medium. Now, we also have got n12, which will be just the opposite, it will be refractive index of first medium with respect to the second, and the relation between the two is this n12 equals to 1 upon n21. So, just need to be careful, n12 is equal to 1 upon n21. So, this is about the refraction, that is the change in the direction of the path or the bending of light. Now, let us more in detail, we will see how is the bending of light as per the medium it encounters. Now, look at it carefully. I have got a rarer medium. Now, rarer medium I can think of a air, denser medium I can think of a water or a glass. So over here the ray hits the interface with a certain angle I, and it is going from the rarer to the denser. When the ray is moving to a denser, the refracted ray is going to bend towards the normal. Always it is going to be towards the normal, and you can check out. So, the angle of refraction is less than the angle of incidence. And why this happens? Why do we get the refraction? That is because the speed of light decreases when it is moving in the denser medium. So, that is the reason why we do have the refraction. Next, so suppose now you can see this is a denser medium, then down is a rarer medium. So, the light is being travelling from the denser to the rarer. So, at this point at the interface it will be refracted, and the ray is going to move away from the normal when it is moving into the rarer medium. So, if this is your angle of incidence, this is your angle of refraction, you can see angle of incidence is less than your angle of refraction. So, in this way you know the speed of light in air and in vacuum is the max, that is 3 into 10 raised to 8 meter per second. So, as it encounters a denser medium, whether it be a water or a glass, the speed decreases from the 3 into 10 raised to 8 meter per second to a lower value. Now, let us see this. So, I have the air, just as I have told you, the speed, and the glass. The speed decreases, and you can see it is 2 into 10 raised to 8 meter per second. Now, the ray has been incident straight, the normal. This incident ray is normal to the interface. Now, what you can say about the angle of incidence? Isn't it 0? The angle of incidence over here is 0, hence there is no refraction, it just goes straight. The speed decreases, but when it is incident with an I 0, it moves like this. So, this is how is the change in the path when it hits the interface. So, let us move on to the refraction through a glass slab. So, I have got the picture, the ray diagram of the glass slab. So, here the ray which is travelling is encountering the interface at two places, that is over here, that is the ray is going to move from the rarer to the denser. Denser is the glass, and at the second point it is going to move from the glass to the air, that is denser to the rarer. So, let us see how the things are happening. So, my ray hitting at the interface, the path will be like this, that is because from the rarer it is going to a denser, and I know it is going to bend towards the normal. So, this is the path of the light, then again it hits the second interface, and now it is going into the rarer. So, the bending is going to be away from the normal. So, I have noted here as I1 R1, that is at the first interface, and next is I2 R2. Now, in absence of glass slab, the incident ray will have travelled like this. So, what the glass slab has done has changed the path, and this is your emergent or the final ray coming out. And you can see, though the incident ray and the refracted, the emergent ray are parallel, there is a lateral shift. So, glass slab has taken the lateral shift. There is no deviation, but there is a lateral displacement. Okay, so, this is how the refraction through the glass slab is. Now, same way we have another phenomenon wherein we get the real and the apparent. Now, this you must have seen, if you have got the bucket of water and if there is a coin which is lying at the bottom, you will feel that it has raised. Over here you can think of as a water, so we will be going from the denser to the rarer, so bending is going to be away from the normal. So, this is actually the real depth where the coin is lying, and this is the apparent what we feel. So, the formula is apparent depth is given as real depth upon n21. n21 is the refractive index of second medium with respect to the first. So, these are the many phenomenon which are encountered, which we encounter, and that is the reasoning is the refraction. There are few more phenomenon. So, let us see some beautiful phenomenon due to refraction. Now, bending of an immersed object. Definitely students, you all must have seen this. What do I have here? I have got the pencil which has been dipped in an water. And what do you feel over here? Don't you feel it is bent? But it is actually bent? No. The pencil is the straight. The answer to this, the bending, is because of the refraction of light. Now next, the advanced sunrise and the delayed sunset. Meaning what? You see the sunrise or the sun a little before the actual sunrise, and you can visually see a sun's little after the sunset. Now what do I mean by actual sunrise? Is the actual crossing of the sun at the horizon. So here you have got the picture. So there is an observer. The picture shows you the apparent positioning of the sun and the actual positioning of the sun. So this is all because of the refraction. So students, you have got why is the answers is all because of the refraction of light. Now let us move on to another interesting factor as about another interesting phenomenon, that is the total internal reflection. It's a beautiful phenomenon, so please concentrate. So what it says, it is the phenomenon of reflection of light when a ray of light travelling from a denser to a rarer is sent back to the same denser medium, provided it strikes the interface of the denser and the rarer medium at an angle greater than the critical angle, and is called total internal reflection. Let us understand it with a ray diagram. Here, isn't it looks very beautiful? So here students, this is a denser medium, it's in water, a rarer medium, air. So I have got an object, you can think I am standing over here and the rays are coming out. So over here, first ray is perpendicular to the interface. I have already explained, it is going to move straight. Now the second ray is incident at the interface with a certain angle I, and we know because it is going from denser to the rarer, the bending is going to be away from the normal, and there you get your angle of refraction. My next ray is been incident with an angle of incident more than the previous. So if this is more than the previous angle, definitely your angle of refraction is going to be more than the previous. So this bending is going to be more away from the normal. So in such a way, I get an angle of incidence over here. I can term it as a critical angle. So at the critical angle point, the angle of refraction becomes 90 and the refracted ray just glides over the surface. I will repeat, the refracted ray is just gliding over the surface, so much so that the angle of refraction is 90 degrees. And now if you increase your angle of incidence above this critical angle, you see that there is no refraction at all. Other than that, the ray is totally internally reflected back in the same medium, and this is total internal reflection. Isn't it something beautiful, student? Though we are moving from denser to the rarer medium, there is a two different mediums, but the moment it strikes with an angle greater than the critical angle, we get total internal reflection. So, the conditions, there are two conditions, an important condition for TIR to happen, and that has been highlighted over here. First thing, your ray has to move from the denser to the rarer, it has to go from the denser to the rarer, and it has to, the angle of incident has to hit with an angle greater than the critical angle. So, this is the conditions for TIR. Now, there is a relation between refractive index and the critical angle. Now, why I have chosen this? You know very well the Snell's law is sin I upon sin R equals to the Ri, that is the refractive index. Now, when the sin I is critical angle, you know R is 90 degrees, isn't it? This is 90 degrees. So, sin of 90 degrees is 1, and hence I have got this 1 upon sin of IC, and we know that N12 is equal to 1 upon N21. So, using all this I am getting the final expression as N12 equals to 1 upon sin of IC. So, this was an interesting phenomenon which is known as the total internal reflection, something really beautiful. Now, let us see where do we use this, or what are the applications of it. We know something really beautiful happening over here, so let us check out the applications of it. Now, the first one, what do I have? It's a, yes, it's in diamond. Isn't it nice, sparkling? Now, this sparkling diamond, the naturally occurring diamond, they do not show any brilliance. Though the diamond are known for its brilliance, the naturally occurring do not show any brilliance. It is the technical skill of the diamond cutter which cuts it in such a way that when the light enters, it suffers the multiple TIR, and finally the light which comes out makes the diamond sparkle. So, you can see over here I have the light which is incident, but at the point we have the TIR which hits the another, again a TIR. So, there is a multiple TIR which are happening. So, this takes into the TIR. Next one is the prism. Now, there are prism which have been designed to bend the light by 90 degrees and by 180 degrees. Again, these prisms takes the help of TIR. So, you can see the prism has been designed to bend the image by 90 degrees and it is of the same size. So, it is hitting at an angle greater than the critical angle, hence it suffers the TIR. Over here it has been designed to bend it by 180 degrees, same over here. So, phenomenon behind this is the TIR. Now, let us see some more. Mirage. Now, what is this mirage? Before going ahead, I will just ask you a question. You are recently travelled in a vehicle by bus or by a car in a hot summer day. What do you see at a distance? You must be getting a feel of a patch of water quite at a distance. But when you actually go, when you actually reach at that spot, there is no evidence of water being there. So, why is it? Why is this happening? The answer is hidden in this. So, let us see the mirage or the optical illusion. Now, what do I have on the screen? It's the picture of a desert. Now, think we have got the thirsty traveler traveling, and he sees the object and the image. So, isn't it he is going to get a feel of a water pool? Poor thirsty traveler will run towards it, but when he actually goes there, there is no evidence of water. This is the mirage. It's an optical illusion. Now, why this is happening? Let's understand. Now, the hot summer day, the land is being heated up, the air near the ground becomes lighter, whereas the air above is denser. So, there is a difference in the density, the optical density. So when the ray of light coming from the tall objects like a tree, so when the light is coming, there are these layers of atmosphere, and you know the density is decreasing. So every time it is going to suffer the refraction. At every layer it is going to have the refraction, and when it hits the ground, if it hits with an angle greater than the critical angle, then the ray is going to suffer the total internal reflection. So the ray is going to be reflected back, and the poor traveler will think that this particular ray is coming from here, as we get an illusion of a straight line. So he will see the object as well as the image, and he will think of a water pool at the side. So he will rush to it, but you know it's just an illusion. There will be no sign of water. So this is all about the mirage. It is the optical illusion of something, but which is not there when you actually go. Let us move on to some more examples. Optical fibers. Now optical fibers have got an extensive use in telecommunication. So let us first see what is an optical fiber. So here, isn't it something beautiful? So these are the fibers. They are made up of high quality composite glass. It has got a core and the cladding. This is the core, that's the cladding, and the refractive index of the cladding is less than of the core. Now how the TIR is happening? You can see over here in the core the light is being incident, and the light suffers multiple TIR, and finally light comes out from the other end. You can have a picture using this, it will be much more clear. You can see the light ray being incident in the core, and you can see the multiple TIR. So this core is in the cladding, and this cladding is in this plastic coating. So the way you have seen, you will have this particular picture. So these are your optical fibers, the optical fibers which are in the plastic coating, and the number of fibers bundled is termed as a light pipe. So this was about the optical fibers. Now as I have already told you, it is extensively used. They are very much important. Why? Because the intensity of light is not lost. The loss in intensity is minimum. Even if you curl it, you turn it anyhow, the intensity is the same. So let us check out the applications of optical fibers. As I have told you, major use is in the telecommunication. To send the signals, the audio and the video signal to a large distances, we make use of the optical fibers. Decorative lamps. Haven't you seen this? Yes, isn't it beautiful? So these fibers are the optical fibers. One end is given an electrical connection, so when you switch on, the light is transferred, and at the tips you can see it glowing. The next application is an instrument known as the endoscope. It is used for the endoscopy. Now this is a medical instrument. Okay, the light pipe is inserted in the patient's body in order to check out the organs, the intestine, the stomach, so as you get a clear picture of it. So here on the screen the doctor can examine the internal organs. So this is the use of the optical fibers. So you know it has been used for a wide range. So students, let's revise what we have done today. We started off with the beautiful things with reflection, refraction. Then we moved on to some magnificent phenomenon. Another interesting or magical phenomenon was TIR, and then we have seen the different uses of the TIR. So students, this is what we have studied for this particular chapter, the half the part, and the still remaining is the lenses, the prism and the optical instrument. So till then students, you stay at home, you stay safe and check out what we have learned. So next time is going to be a more beautiful thing. So thank you students, thank you very much.
Prudent Scholars, powered by Lupin Pharmaceuticals.
अब आपकी सुरक्षा आपके हाथों में। ल्यूपी सेफ हैंड सैनिटाइजर, आपका और चेन्नई सुपर किंग्स का फर्स्ट लाइन ऑफ डिफेंस। अब आपकी सुरक्षा आपके हाथों में। ल्यूपी सेफ हैंड सैनिटाइजर, आपका और चेन्नई सुपर किंग्स का फर्स्ट लाइन ऑफ डिफेंस। अब आपकी सुरक्षा आपके हाथों में। ल्यूपी सेफ हैंड सैनिटाइजर, आपका और चेन्नई सुपर किंग्स का फर्स्ट लाइन ऑफ डिफेंस।